Hello, my name is Lorena, and today we are going to use partial fractions to find the integral of 1 over x minus 2 times x squared plus 2x plus 2. Briefly, we are going to rewrite our function as a sum of quotients, and then we are going to find the final answer by adding up simpler integrals. We are going to solve this exercise in 4 main steps. First, let's factor out our denominator. So we are going to rewrite x minus 2 times x squared plus 2x plus 2 as a product of terms that are irreducible, and irreducible terms are the ones that are either linear, like x minus 2, or quadratic equations that are not decomposable into real numbers, and those are the ones that have no real roots. We will see that the one we have right here is one of those. X squared plus 2x plus 2 equal to 0 doesn't have any real roots because according to the quadratic formula we have that those roots would be minus 2 plus minus the root of 2 squared minus 4 times 1 times 2 over 2 times 1, and that equals minus 2 plus minus the root of minus 4, that's 4 minus 8 over 2, and that's not going to be real. So it's going to be imaginary roots. Once you have imaginary roots, you don't have to decompose your quadratic equation further. And once you are done with all the quadratic equations and you have them as decomposed as they can be, you go to the step number 2. So now we are going to set fractions based on our decomposition. Fractions depend on factors, and you will have as many fractions as factors. Let's count the factors we have. X minus 2 is raised to the power of 1, so that's one factor. And the quadratic equation is raised to the power of 1 as well, so that's another factor. In total we have 2 factors, then we will get 2 quotients. And what we do with those is set the function, the original one, so that's 1 over x minus 2 times x squared plus 2x plus 2 equal to the sum of those quotients. The first quotient is going to be related to x minus 2, and it's going to take the form number to be found, that's a, divided by x minus 2. Factors always go at the bottom, and when you have a linear factor you will get a constant on top. The second quotient is going to be associated with the quadratic equation, and it's going to take the form linear term, so it's going to be bx plus c, b and c to be found, divided by the quadratic equation x squared plus 2x plus 2. The factor itself goes at the bottom, that's always the case, and for quadratic equations you will get linear terms on top. Okay, once you set the equation, you go to the third step, in which you find the values of a, b, and c, and any other constant involved in your decomposition. We're going to find a, b, and c that make this equation in part 2 valid. So we're going to force 1 over x minus 2 times the quadratic equation to be equal to the sum of the quotients on the right-hand side. And the sum of the quotients on the right-hand side is going to be another quotient. Its denominator will be the common denominator, and in this case we will have the product because those terms have nothing in common. And on top, we will get the cross product of numerators and denominators because of the way we had to find this common denominator. So we will get a times x squared plus 2x plus 2 plus bx plus c times x minus 2. Then you can see that 1 over x minus 2 times the quadratic equation has to be equal to something that contains a, b, and c divided by the same product, x minus 2, by the quadratic equation. Then, necessarily the top parts match, so 1 has to be equal to a times our quadratic equation, x squared plus 2x plus 2, plus bx plus c times the linear factor x minus 2. Or, same thing, 1 equals a plus b times x squared plus 2a plus c minus 2b times x and then plus 2a minus 2c. That comes from expanding all the products on the right-hand side of the first equation I wrote, and from gathering all like terms. I'm going to highlight these equations. The first one is going to be in yellow, and the second one is going to be in blue. And both equations are the same, just written differently, and they have to hold for all values of x. So this is true for all x in the real numbers, for all x positive, negative, and x equal to 0. Now I am going to use both equations, the one in yellow and the one in blue, to find a, b, and c. To find a, I will make x equal to 2, and I will see what happens in the first equation when I do so. So I see that 1 has to be equal to a times 2 squared plus 2 times 2 plus 2, and then plus b times 2, so that's 2b plus c, times 2 minus 2. When x equals 2, the equation in yellow becomes 1 equals a times all the things with x equal to 2 plus b times x equals 2 plus c times 2 minus 2. And as you can see, the second term is going to go away because we are multiplying it by 0. We are getting something times 0. So we will end up with the first term only, that will be 10 times a. 10 is 2 squared plus 2 times 2 plus 2. And if 1 equals 10a, then a equals 1/10. Alright. Next, I am going to make x equal to 0. And I take 0 because it's an easy choice. You don't have to take the value 0. You didn't even have to take the value 2. It just makes things easier. But you choose what you like. When I make x equal to 0, and I look at the first equation, the one in yellow, I find that 1 has to be equal to 2 times a minus 2 times c. And I have a, so I can actually solve for c from this equation to find that c equals 2a minus 1, all of that divided by 2. And 2a equals 2/10, and that will be 1/5. And then I subtract 1 and divide by 2 to get c. So c is going to be minus 4/5 divided by 2, because 1/5 minus 1 equals minus 4/5. And when you divide by 2, you get minus 2/5. By using the equation in yellow with x equal to 0, I found an equation that involves a and c. And since I have a, I got c. Alright, next I am going to use the equation in blue. And I will use that one because if I make x equal to something else, I will get an equation in a, b, and c, and that's kind of long. So instead, I will use the second equation, and I will exploit the fact that two polynomials are the same if and only if coefficients match. So the polynomial we see on the left-hand side in the equation in blue, that's 1, has to be equal to the one on the right-hand side. And then the polynomial of x squared on the left-hand side has to be equal to the polynomial, the coefficient of x squared on the right. So we have to have that 0. That's the polynomial of x squared, because we don't see any on the left, has to be equal to a plus b. That's the coefficient of x squared on the right. So this comes from matching coefficients. We could also choose 0 equals 2a plus c minus 2b, and that's going to be fine. It's going to contain a, b, and c, so it's kind of long again, but it's up to you. If you choose 1 equals 2a minus 2c, you won't get anything new because that's actually the equation you used when you made x equal to 0. So you better choose something that contains the unknown, and that's b. So 0 equals a plus b, and a equals 1/10. That implies that b equals minus 1/10. So I used the first equation for finding a, the same equation for finding c, and then I used the equation in blue for finding b. You can use a combination of both techniques. You could reduce to one of those techniques as well. It depends. It's up to you. It's just a matter of choosing what makes your life easier. Alright, once you have the value of those constants involved in your decomposition, you go and find the final answer. So you compute the integral of 1 over x minus 2 times x squared plus 2x plus 2. Maybe we write it more nicely. So we have x squared plus 2x plus 2. Yeah. And to do that, I am going to replace the function 1 over x minus 2 times the quadratic equation by its decomposition, the one I found in steps 2 and 3. So I'm going to rewrite this integrand, the function to be integrated, as a, that's 1/10, divided by x minus 2, plus, and then we have b, x plus c, so that would be minus 1/10. I'm just looking at the values I got in part 3, so that would be minus 1/10 minus 2/5 divided by the quadratic equation. And now I am going to distribute the integral. Integrals are linear. If you have the integral of the sum, then you get the sum of the integrals, and also you can pull out constants. The same with subtraction. So we will have that 1/10 can be pulled out to get 1/10 of the integral of 1 over x minus 2. And then from the second addend, I will get two fractions because I can distribute the denominator, and I will get the minus 1/10 pulled out times the integral of 1 over the quadratic equation. Oops, and I forgot an x. So let me insert it here. We had minus 1/10 of x minus 2/5. Sorry about that. So we have instead x over the quadratic equation. And then the third integral is going to be minus 2/5 of the integral of 1 over the quadratic equation. Alright, so now you can see that we reduced the problem to finding integrals of fractions that look easier. Fractions that look kind of simple, at least simpler than the initial one, the original one we had. And now at this point I am going to find each of those integrals you see separately, and then I will insert the outcome into the equation. So let's insert the outcome into the chain of equalities we have. Let me start by finding the integral of 1 over x minus 2. The integral of 1 over x minus 2 is very similar to the one of 1 over x. It kind of looks like it. So that suggests we should take the substitution u equals x minus 2. So du will be equal to dx, and then this integral in terms of u will be the integral of du over u. And the integral of 1 over u equals the ln. So we'll get the ln of the absolute value of u plus a constant c, let's call it c1, and that corresponds to the ln of the absolute value of x minus 2 plus c1. And it's very important for you to go back to the variable x because that's the one you had at the beginning. The antiderivative of a function with x can't be something with another variable. You have to go back to x. So I am going to write here 1/10 of what I just found. So it's the ln of x minus 2 in absolute value plus a constant I called c1. Next, I would like to find the third integral, and I will find that one before the second one because I will need it for the second one. So I will find first the integral of 1 over the quadratic equation. So that's integral of 1 over the quadratic equation. I am erasing each time so I have enough space. And let's see how this one is solved. Okay. To find this integral, we have to rewrite the denominator, that's the quadratic equation we could not decompose, as a binomial squared plus or minus a number. In our case, we will actually have a plus. We can actually rewrite the denominator as x plus 1, all that squared plus 1. It's probably easier to go from the right to the left, because when you expand x plus 1 squared, you get x squared plus 2x plus 1. And then when you add 1, you get the plus 2. Anyway, you have to go from the left to the right, and the trick is to take half of the coefficient of x and put it besides plus in the binomial. So we have x plus 1, all that squared. So this one came from taking 2 divided by 2, and this 2 is the coefficient of x. And when you expand x plus 1 squared, the constant term will be 1. And we need a 2, so we have to add 1. Alright, so that's how we get that. And that's very useful, because then you can see that this integral is kind of similar to the one of 1 over x squared plus 1. So it kind of looks like the integral of 1 over x squared plus 1. And we know that this integral is arctan. It's going to be an arctan. It's going to be the arctan of x plus some constant. So this suggests we should use substitution. And the substitution we are going to introduce will be precisely u equals x plus 1. So you can see that it was very important to rewrite the quadratic equation in terms of a binomial square, so you could see the substitution you need, the one that is going to be useful. Because when we make u equal to x plus 1, then everything is reduced to very simple things. So du is going to be equal to dx, and when we rewrite everything in terms of u, it will be du over u squared plus 1, and we know that this integral is an arctan. So we get the arctan of u plus a constant, and I'm going to call this constant C3, and 3 because we are going with the third integral right now. So this will be the arctan of, and u equals x plus 1. Remember, it's very important to go back to x because that's the original variable, and we have indefinite integrals. So we always have to go back to the original variable, and then plus C3. Alright, so now I am going to replace the third integral by what I just got, and I'm going to leave some space in between because I need the result of the second integral. So I put here minus 2/5 arctan of x plus 1. Let me write this x plus 1 more nicely. So we have x plus 1, and then plus C2. Alright, so now we know what the integral of 1 over that quadratic equation is equal to. We are ready for finding the second integral, the one with x on top. So we're going to find the integral of x dx over the quadratic equation x squared plus 2x plus 2. To find this integral, again, we are going to rewrite the denominator in terms of a binomial squared, so we can see a substitution more clearly. And now you note that we have x plus 1 at the bottom, and that suggests a substitution, but we don't have it on top. So we can fix this. We can rewrite x as x plus 1 minus 1. We're just adding 0, and we divide it by the same quadratic equation. And I had missed a dx. And now we distribute this integral to get the integral of x plus 1 over x plus 1 squared plus 1, and then minus the integral of 1 over the quadratic equation, and I am going to expand the quadratic equation because I don't have to do anything with it. I have this integral already. Okay, so we don't have to worry about this term because we have it. That's what we computed when we were dealing with the third integral, but we have to work harder on this term. Okay, so what I'm going to do is to take a substitution, and I'm going to take u equal to x plus 1 squared plus 1, and you will see why. What will happen is that du will be twice x plus 1 times dx so I have part of du on top in this integral. When I rewrite this integral in terms of u, I find that it equals the integral of, and x plus 1 times dx corresponds to du over 2, so du halves, and then we have a divided by u. And then we get the minus the integral we found before, so that would be arctan of x plus 1 plus c2, and the integral of 1 over u is ln of u again, and we have a half in front of it, so we get 1/2 of the ln, and u this time is the quadratic equation when you expand it. And then you have minus arctan. So let me shift this to the left. And we do this magically with one note. That's wonderful. And so we get the minus arctan. It's very short anyway. Have to shift it a little more. Yeah. So it's going to be minus arctan of x plus 1. And then we have this minus c2, and we get this minus c2. So the second integral is found by fixing the numerator, so we include the same kind of expression we see in the denominator. So we use a substitution that will work, and we get this extra term we didn't see at the beginning, this minus 1 over the quadratic equation, but we're good with that because we found its integral already. So I am going to replace the second integral by this whole thing. So that's going to be, and again I will have to shift my things a little to the left because it's kind of small for that. Okay, so it's going to be minus 1/10 times this whole thing we found for the second integral. So we will have a 1/2 of the ln. So it's 1/2 of the ln of our quadratic equation. Then minus arctan of x plus 1, and then minus c2. So that looks busy, but it is what it is. Alright, so now I'm going to erase everything I did for this integral. I hope you took notes of it. So we have it there. And now we're about to get the final answer. We have some constants floating somewhere around here, and I will make a comment about that in a minute. First, let me rewrite this product. So let me just distribute everything. So I get 1/10 of the ln of x minus 2 in absolute value, and then minus 1/10 of 1/2 of the ln, so that will be minus 1/20 of the ln of our quadratic equation. And then we have minus 1/10 times minus arctan, so it will be plus 1/10 of arctan of x plus 1. And then we have the minus 2/5 of the arctan of x plus 1. And then we get these constants, 1/10 C1, and then minus 1/10. And oops, I had missed this one. I think this one was before. It was supposed to be after. So we have plus 1/10 of C2. And then we get this minus 2/5 of C3. And of course I don't have to write all those constants there. I just wanted to make sure that you see how the final constant will come. 1/10 of C1 plus 1/10 of C2 minus 2/5 of C3 equals another constant. Those constants are arbitrary. We have no definite integrals here. So we just can't find those constants. We don't have to use them at all. We just gather them all in one single constant, so we call it just C. And we can see that we have some like terms because we have arctan of x plus 1 in two different places. So we're going to gather them as well. So the final answer will be 1/10 of the ln of x minus 2 in absolute value. And then we have the minus 1/20 of the ln of this quadratic equation. And maybe you didn't notice it before, but I didn't write any bars around the quadratic equation because it's already positive no matter what x is. When quadratic equations have no real roots, they take one single sign, and this one is positive because the leading term is positive. Alright, and then we have the plus 1/10 minus 2/5. So that's going to be 1/10 minus 4/10. So that's minus 3/10, right? Times the arctan of x plus 1. So that's it. And then we have this plus c. So let's just make sure we got the right thing. We're finding the integral in this fourth step, and we replaced the function by its decomposition, and we used the values a, b, and c we found. So that's a over x minus 2, that's 1/10 over x minus 2, and then plus bx plus c, that's minus 1/10 minus 2/5 over the quadratic equation, dx, and then we distribute the integral sign to get 1/10 1 over x minus 2 in this integral, and then minus 1/10 integral of x over the quadratic equation, and then minus 2/5 of the integral of 1 over the quadratic equation that came from using the linearity of integrals. You can distribute integrals when you have sums or subtractions, and you can also pull out the constant without any problem. The first integral was found by using substitution. We used u equals x minus 2, so we got the integral of 1 over u, and that's ln of u. So we got 1/10 of the ln of x minus 2, that was your u in absolute value, plus c1. Then we found the third integral by using a substitution, and this time we rewrote the quadratic equation as a binomial squared plus a number, and we found that this integral was similar to the integral of 1 over u squared plus 1. Well, 1 over x squared plus 1. That's how it looked like after we replaced everything or substituted u in it. And we got an arctan of u, and u was x plus 1. So that was arctan of x plus 1, and then we have this constant that appears every time you have indefinite integrals. And then we used that integral to find the integral of a more composed function, and that was x over the quadratic equation. And we had to fix the plus 1 first. So we got So we got out the integral of x plus 1 over the quadratic equation, and then minus the integral of 1 over the quadratic equation. So we reduced everything to applying a substitution again, and we got a ln. So that would be a ln of the quadratic equation, and there was a 1/2 in front of it that came from the substitution from finding du in terms of dx. And then we also used the integral of 1 over the quadratic equation we have found, and we added this constant that we always have when we integrate, when we have indefinite integrals, and then we gathered all the terms. So we had the ln with x minus 2 in absolute value, the ln of the quadratic equation, and then we could gather the terms with arctan, which were plus 1/10 minus 2/5 of arctan. Also, we gathered all the constants because they were all arbitrary, so we could just put them all in one single constant that we called c. So that's it. We have the final answer. Let me highlight it in green. And to summarize, we were finding certain integral by using partial fractions, and we solved this exercise in 4 steps. First, we decomposed the denominator, and we made sure that our quadratic equation was undecomposable by showing that it doesn't have any real roots. Second, we set our decomposition based on the partial fractions. Third, we found constants involved in the decomposition. And fourth, we found our integral by adding up some integrals that look easier and that were found by using substitution. This exercise was a little long, and the fact that we had this quadratic equation and that we had 3 terms made it even longer. But that's pretty much the general idea for solving any type of exercise of this type. So any type of exercise like this, like when you have a linear term and a quadratic equation. So I hope you make the most out of this video. Please make any comments or suggestions, and I will see you the next time. Bye bye.